Right. So here's my little story for you guys today. My story is called Organic Chemistry for Babies. And I know it says for babies. A lot of people complain about organic chemistry, like babies. But it is a really good book to explain to you guys the basic foundation of what organic chemistry is and why. So, the first thing we're going to think about is a ball. So, this is a ball. This is a ball. This ball can stick to 2 other balls. You don't like it? It's going to get better. All right. This ball can stick to 3 other balls. See a yellow ball, and there's 3 blue balls now. All right. And this ball can stick to 4 other balls. So it's kind of like you guys looked at this in structured bonding when we were talking about shapes and things. So this is a red one, and we got 4 blue ones. All right. So each type of ball can stick to a certain number of other types of balls. Yeah. All right. Imagine all the shapes we can make just by combining these balls together. Yeah, that looks like a caterpillar. It looks like a very hungry caterpillar, but we're not doing that story today. All right. These balls are like atoms, and atoms make up everything. Each type of atom can stick to a certain number of other atoms. This is a carbon atom. It is very special. It can stick up to 4 other atoms. And it sticks very well. So do we see here? That was a very loud screech from us. So there's carbon, there's some carbon, there's some carbon, and all those carbons, you'll notice that they are bonded to 4 other things. And it likes to make big shapes. It's pretty, huh? All right. These shapes are called organic molecules. And there are many organic molecules. With the analogy? Some are medicines. So this one's aspirin. Take that when you have a headache. Some smell really nice. So we have one that's the vanilla. So all these little like corners here that aren't labeled with a letter, that's carbon. And so we're just seeing how that carbon's bonded to other things. Cool. It's a very good building block. Organic molecules are found everywhere. And there's some really good examples here. We have amylose, which I believe is a sugar. You have some soap. You have some amino acids, which you guys are learning about in biology. There's cotton, which is a polymer. Gasoline contains lots of organic molecules. So here's an example of some gasoline. And again, you can't see the carbons right now, but you can see that they're bridging off quite a bit. So really, really good building block. Plants contain lots of organic molecules. So you guys are learning about plants in biology again. This is chlorophyll, which is what's responsible for converting that light energy into chemical energy. Glucose is the sugar that we store that energy in. Glucose is a sugar. So you see, organic, lots of molecules. Even you contain lots of organic molecules. And you can see there's a person, and then some examples of stuff that we are made up of. All life on Earth has organic molecules. All life on Earth has organic molecules, and all life on Earth needs carbon. And now you know organic chemistry. You're ready for your external. No, it's just a foundation. So the thing to think about for organic chemistry that makes it really, really important is that we are talking about carbon chemistry. Carbon is what we call the king of all elements because it can do so many bonding kind of options and patterns. And that's what you were supposed to hopefully see in that little picture book. If you guys remember, when we talked about the periodic table, there were certain trends and patterns. I'm trying to find one now. Here we go. There are certain trends and patterns in our periodic table. So for example, when we are talking about, say for example, group number 1, Their valence shell has only one electron. You guys remember that?
Yeah.
And so since it only has one electron, it will the easiest way for it to be stable is to lose that one electron and gain a positive one charge. Beryllium and group 2, they want to lose 2 because they have 2 valence electrons. When we go to group 13, they have 3, so they're going to lose 3. When we go in the other direction, group 17, 7, gaining 1 will be the easiest way to be stable. 16, gaining 2 is going to be the easiest way to be stable. Group 15, gaining 3 is the easiest way to get stable. Now, group 14 is really, really special because group 14 is in a situation where it can gain 4 or lose 4. So instead of doing that and forming ions, group 14 tends to form more covalent bonds. So they share electrons to get up to their 8. So items in group 14 will then be capable of doing the maximum number of bonding, which is 4. If I'm looking at nitrogen or oxygen, I'm limited in how many bonds that I can make. Nitrogen is limited to only doing 3 bonds, and oxygen is only limited to 2. And you guys would have learned this when we were talking about Lewis structures. How many bonds can each one have? Carbon is one that can have multiple bonds. So since carbon has maximized the number of bonds it can make, it is a very good building block, and that's why we call it, like organic chemistry, we refer to it as kind of the chemistry of life. It is the building block for a lot of things. Carbon's also the smallest of the atoms in group 14. In theory, we could have silicon-based life forms. You might have heard that being talked about as a potential kind of sci-fi idea, where silicon, because it can do those 4 bonding, is then the building block to making life. Haven't seen it yet. Probably not going to happen because it's not as readily available. Carbon is most likely what we're going to find as our life forms. Again, there is talk about maybe we'll find nitrogen-based life forms, but you won't be able to make as complicated molecules because you are having 1 less bond potential because they can only do 3. So that's why carbon is super duper important. Are we good so far? All right. So all of our chemistry is going to be focused around carbon and what it can do. So let me just check my to-do list of stuff we were going to talk about today. Notes on alkanes, and then you guys have a SciPy page to do. Right. So let's talk about what organic chemistry is. I don't need that many pieces of paper. All right. So here are some notes for you guys. So move that a little bit closer. Organic chemistry is all about carbon. And carbon is a really special element because carbon can have the maximum amount of bonds compared to other things on the periodic table. It can have 4 bonds. So it's making it a very good building block, a very good Lego. Are you okay with that so far? All right. What else do I want to add? So when we were talking about organic chemistry, there are also other molecules that can come into play that can bind with carbon. They do this through covalent bonds to make these kind of compounds. These include, other elements. Include oxygen, nitrogen. What else do we normally see in a lot of those guys? You might see sulfur and phosphorus. And then the halogens are very common to see. So the reason why is because those guys can do covalent bonds. So when you think about oxygen, it can have the place for 2 bonds. So we normally, you can see, say, for example, carbon dioxide. That's an example of something that it can be bonded with. So I'm looking at things that can form covalent bonds. With sulfur? I think it's usually, just like that, and then whatever else is bonded to it. Usually something like that. Can't remember how many things sulfur is bonded to, but you see sulfur a couple times. What we're looking for basically is the nonmetals. So these ones are going to be doing covalent bonds to build the compounds. Use compound because it's a better word. It's more open-ended. All right. Are we okay with that so far? Keep going. Okay. So there are lots of different categories when we're talking about organic chemistry. We refer to them as functional groups. So we're just talking about what sort of characteristics does that organic molecule have. The first type of functional group that we're going to talk about, and we're going to talk about this over the next couple of days before I introduce some more, is the alkanes. So alkanes, that is an example of a functional group. And I say that kind of loosely. And these ones are the simplest. When it comes to the organic molecules. Alkanes are also known as, or they are, I should say, hydrocarbons. What do you think hydrocarbon means?
Water.
You're close. There's something in water that I want. The hydrogen. So if we break up the word, it's made up of only hydrogen and carbon. So the only thing in that molecule will show hydrogen and carbon. If you have other substances like oxygen, then we're starting to talk about different categories of functional groups. So we look at alkanes because alkanes are the simplest of the list. All right, keep going. Okay. So when we are thinking about alkanes, we have to think about the number of carbons that are there. So say, for example, if I only have one carbon and the rest are all filled with hydrogen, that's a one carbon chain. And I will call that methane. The A-N-E ending, that ending tells you the functional group is an alkane, which makes sense. A-N-E, A-N-E. So if I see methane, that's just telling me alkane. Cool. If I have a two carbon chain, let's say I have two of them added together, like that. So two chain, that is ethane. I'm just underlining the ane so we can see that that's the pattern. Now I'm drawing a three carbon chain. What do you think I call a 3-1? Propane. If you watch King of the Hill, he talks about propane and propane accessories. It's a flammable gas, no? Okay. Well, it's on Disney Plus if you guys want to watch it. All right. 4. 1, 2, 3, 4. It's going to put the hydrogens in. So we have to remember hydrocarbons. If I have 4, that's butane. Ethane.
Okay.
Third one's propane. Fourth one's butane. Fifth one you might be able to guess. What do you call something that has 5 corners? Pentagon. So that should be pentane. Yeah, you might have heard of butane gas. We burn that. So if it's 5, that's pentane. Need the devices.
Okay.
Pentane. Yeah, 1, 2, 3, 4, 5. Pentane. What do you think 6 might be called? Hexane. Yeah, so some of the numbers you have heard before. Yeah, 6, 1, 2, 3, 4, 5, 6, yeah. Now I'm putting in all the hydrogen so you guys get into the habit of it. So if I have 6, we call that hexane. If I have 7.
7.
That's, I can see why you say that. 7 isn't as obvious.
Octo.
You're getting there for 8.
Octane.
Octane for 8. All right. If I have 7, I call that heptane. All right. Now I'm getting longer. Now I'm getting to 8. 1, 2, 3, 4, 5, 6, 7, 8. Starting to get squished in now. What do you think 8 is?
Octane.
Octane. Oxygen. No, oxy. I'm only going to go up to 10. You won't be going up past 10.
11.
Octane. My hands are hurting. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. What do you guys think it's going to be called?
9.
9. Yeah, is there anything September related maybe? Septane. Septane. My hand really hurts now. There's 2 9. All right, 9. Non-name. Like no name. All right, and then 10. What do you think it is? Cooking. Oh my god, you can tell I'm just like losing my mind drawing all these H's.
Heptane.
Heptane? Oh, we already have a heptane. Dectane, you're right.
Decatane.
Could you think about a decacong?
The shape of
Alright, so 10 is decane. Think about the word decade. So some of them you will be able to pick up because like you can recognize it through like math and talking about octagons and octopus. Some of them you won't because the language hasn't translated over. But those are we only have to worry about up to 10. You're not going to have to worry about past 10. Yes?
Lena?
She's not here.
Oh, that's a straight.
She's supposed to be here. I don't know where she is.
Okay, cool.
Yeah. All right. Cool. Happy with that? All right. I want to pass out a worksheet for you guys.
Oh.
And I will also be doing it as an example so you guys can start learning the vocabulary when we are talking about this stuff. Here you go. I know it's a big packet, but I just want to make sure you guys have the space to write.
It's so big.
All right. I just want to point out some things to talk about so you guys are aware. Once.
Miss, can we get
There should be 4 there. Fine. Pass her around. Don't be a hoarder. Not crying, eh? So much trouble. Okay, so, there we go. Okay, some things that I need to teach you guys about organic chemistry. So, what I have drawn here with the extensions with all the hydrogens, that is known as your structural formula. So that is showing where everything is bonded and things like that. So, for example, if I was drawing the structural formula of methane, it would just be that same thing that I've been drawing on that piece of paper. Like that. It's going to be hard to fit octane and things in there, but that's okay. The other 2 things that you need to be mindful of is stuff called molecular formula and condensed structural formula. So molecular formula is just you going through and counting up all the carbons and all the hydrogens that are in that molecule. So if I look at my first example here, I have 1 carbon, and I have 1, 2, 3, 4 hydrogens.
Sorry.
Methane, 1 carbon, 1, 2, 3, 4 hydrogens. That's the molecular formula. So all I'm trying to do is just condense down the number of each element. So ethane, 2. And then when it comes to the hydrogens, 1, 2, 3, 4, 5, 6. Cool. So that's what molecular formula is referring to. Condensed formula is like the structural formula, except instead of branching out all my all my hydrogens, I just condense it down to write CH3. So for example, for methane, I would just write CH4. So kind of similar to what I have as my molecular formula. For this case here, ethane, if I wanted to show it as fully branched, I would do that. Show the full structure. If I want to condense that down so it doesn't take up too much space, I would be writing CH3 to show that first carbon, 3 hydrogens attached to it, and then the second carbon, 3 hydrogens attached to it. So that's what the condensed structural formula looks like. It just basically means I don't have all my hydrogens floating around.
So if it doesn't fit, we don't have to do the...
No, you don't have to do the structural ones. Yeah. So I am happy considering I have done the structural formulas for all the notes. If you guys want to go through and just do the molecular formula and the condensed formulas, because it's good practice. Okay? I'll let you guys get that done, and then I'll talk about some other things for organic. All right, so let's go through the next part of the notes, which is starting to name our starting to draw our organic molecules. I figure it's actually easier to go from name to drawing than drawing to name, so that's why I'm doing it in this order, but I will teach you guys in both orders. So, some things to keep in mind when we're talking about organic chemistry is that you have things called the parent chain, which is, I'm going to grab my notes from earlier, so add to them. Steal the notes back, so add to them. Alright, so some things to keep in mind with organic chemistry is that we have things called parent chains and side chains, or known as branches. So you have parent chain, and then there's side chains. You might also hear them being referred to as branches, like a tree. All right. Parent chains we identify in one of 2 ways. The first way we can identify them is that they're the longest chain. The other way we can identify a parent chain is that it has a functional group. Now, in this case, I'm going to refer to things, when I say functional group, it's like special functional groups. So things with like oxygen or nitrogen and stuff like that. We will worry about that in next week's lessons probably. Mainly, all I want us to kind of focus on with the parent chains is that they're the longest ones, is that we're looking for. With the side chains, we have special little nicknames for them. It is based off of the length of that carbon chain. And again, it's all pretty logical. So if I have a side chain with only one carbon, we would call that side chain methyl. If I have a side chain with 2 carbons, we will call that ethyl. If I have a side chain with 3 carbons, we'll call that propyl.
So we just remove the N.
Yeah, so we just remove the A-N-E and we add a YL. Okay? So that's the first thing to keep in note when we're talking about this. It's very unlikely you're going to get side chains that are longer than that, because usually once they're longer than that, then that's actually part of the main chain. So do kind of keep that in mind. The other thing to keep in mind about side chains is that we could have multiple of them. So, for example, with this guy here, my longest chain is 1, 2, 3 propane. So that's where that's coming from. And then I have 2 branches coming off. Those branches are only 1 carbon long. So since those 2 branches are only 1 carbon long, I call them the methyl grouping. Methyl. So where does the di come from? The di is referring to the fact that you have 2 methyls. So I have 2 methyl groups, and the numbers in front tell me where the methyl groups are located. So it tells me that it's located on carbon number 2. So one of the things you have to keep in mind with organic chemistry is that we number the parent chain, and we only number it once. So this guy's 1, 2, 3. So these 2 methyls coming off is known as 2,2-di, because there's 2 methyls. So 2,2-di-methyl, and then propane for my longest one. Are we okay with that so far?
Yeah.
All right, looking at this example here, again, we're just hunting around for the longest chain. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's a lot of ways I can get to 5. It doesn't matter which route I take for my 5, because the other branches will always fall in the same spot then. I know. But we see longest chain, pent. Actually, should I won't go into too much detail with that. Let's not worry about that one, because that one's a little bit complicated. Let's just focus on trying to take the name and draw from the name. Okay? I don't want to get you guys stuffed into drawing to naming. So in that first example, we have 2,3-dimethylpentane.
Hey, what's the numbers?
I'll go over it again. It's positions.
Right.
Bathroom. All right. Cool. So when it comes to naming, we look at the N, and that tells me the parent chain. The parent chain has 5 carbons. So I'm going to draw my 5 carbons. 1, 2, 3, 4, 5. I then see that there are methyls, and it tells me that the methyls are coming off carbon number 2 and carbon number 3. So I can number this in either direction. I can number it from left to right or right to left, but I number it once.
Oh, so doesn't matter.
Doesn't matter. So I'm going to label it this way.
Okay, let's label it that way.
So on carbon number 2, I'm going to have another methyl coming off of it. In carbon number 3, I will also have another.
Does it matter if we go
Up or below? No. Not in this case. All right. And the last thing I do is I fill in the hydrogens. So I can write it like that. It's a little bit squished together. That is showing your structural formula. I'm happy if you want to condense it down so that way it fits better. So you can write it also as CH3CH with a branch coming off CH3. I'm happy with that as well. So I'm happy if you want to do it like that. Either or is fine.
I did the actual.
So this one here is just the condensed structure. Yeah. All right, do you guys need to see another example?
Yes.
Yep. All right. Do you want me to do the heptane? Because that one's different from the pentane. The harder one? All right. Heptane. Hept is what? What number? 7. So 1, 2, 3, 4, 5, 6, 7. And then it says I have a trimethyl. So how many methyl groups do I have? 3. Because tri means 3. Tricycle. All right. They are on carbon number 2, carbon number 2, and carbon number 3. So again, choose the way you want to number it. I'm going to number it from left to right because that's just the way I like to think. So on carbon number 2, I'll have another carbon bridging off. Carbon number 2, I'll have another carbon bridging off. Whoops, getting too excited. And then carbon number 3, I'll have another carbon bridging off. Cool. And then I put in the hydrogens. So I know the methyls coming off will be CH3s. Carbons on the end are CH3, unless they have... most carbons will have 2 hydrogens. Carbon number 2 is not going to have any hydrogens because it's already got 1, 2, 3, 4 bonds. Carbon number 3 has 1, 2, 3 bonds, so it's only going to have the 1 hydrogen. Everybody else has 2.
Wait, what?
Backtrack. So Klein, carbon number 2 already has 4 bonds because it has 1, 2, 3, 4 carbons attached to it. So there's no hydrogens on that one because carbon can only hold 4 things. So the hydrogens are just being added as fillers. The third carbon here, I see it has 1 carbon bonded here, a second carbon bonded here, and then the third carbon bonded up there. So there's only space for 1 hydrogen to get up to 4. And then carbons 2 through 6 each have 2 hydrogens, and then the end carbons have 3.
Wait, are you doing this? You don't do this. Wait, am I doing this? Fine.
Yes, because you need to know it for the,
Ask your question is yes.
you need to know it for spec. Yeah. Spec is our next internal. All right. I'll leave you guys to it. That's what I want you working on now. I'll combine check.